There is a number you have never thought about, a number so fundamental to your existence that removing it would unmake every calendar ever written, every clock ever built, every civilization ever raised from the dust. That number is 24. 24 hours, the length of a day, the time it takes for the Earth to complete one full rotation on its axis, a motion so ancient, so relentless, so perfectly woven into the fabric of life on this planet that no species alive has ever experienced its absence. The tides rise and fall by it. Seeds know when to push upward through the soil by it. Your own heartbeat, your hormones, the rhythm of your sleep, all of it is synchronized at a biological level to the turning of this world beneath your feet. You have never questioned it, neither have I, neither has anyone alive, until now. In laboratories so precise they must be isolated from the vibration of passing trucks, from the footsteps of the scientists who work inside them, from the subtle trembling of the ground caused by ocean waves breaking against coastlines thousands of kilometers away. In these laboratories, physicists operate clocks that do not measure time the way you and I experience it. They measure it the way the universe itself seems to keep it, through the oscillation of cesium atoms, ticking at 9,192,631,770 cycles per second. These are atomic clocks, and they are so accurate that they would not gain or lose a single second over 300 million years. They are, for all practical purposes, the most perfect timekeepers that human ingenuity has ever produced, and they have been telling us something strange. Something that, if you allow yourself to sit with it for a moment, is genuinely disturbing. Not in the way that horror disturbs, but in the way that vertigo disturbs, the way standing at the edge of something vast disturbs. Because what these clocks have been registering over the past several years is that the day is not 24 hours long. Not exactly, not consistently. The planet is rotating, that part remains true, but the rate at which it rotates is shifting in ways that our most sophisticated models of Earth's interior did not fully predict, in directions that even now resist clean explanation, and at a pace that, measured in the only currency that matters to atomic precision, has begun to accelerate. The days have been getting shorter, not by minutes, not by seconds, by milliseconds, fractions so small that no human nervous system could ever register them, fractions that would be invisible even to the most finely calibrated mechanical instrument of a century ago. But invisible is not the same as inconsequential. Invisible is not the same as stable. And when you begin to track these milliseconds across months and years, when you line them up against decades of historical data and watch the pattern that emerges, something becomes undeniable. The Earth is speeding up. The planet is spinning faster than it has in at least half a century of careful atomic measurement. And in June of 2022, the shortest day ever recorded since atomic timekeeping began was logged, a day that fell 1.59 milliseconds short of its expected length. 1.59 milliseconds. Write that down. Hold it. Because that number, that almost impossibly small number, is the crack in the foundation of something we assumed was permanent. Now consider what a millisecond actually is. It is 1,000th of a second. It is the time it takes light to travel approximately 300 kilometers. It is shorter than the time it takes a neuron to fire, shorter than the interval between one frame and the next in a film playing at standard speed. A millisecond is, by any human standard, nothing. And yet the scientific and technological infrastructure of modern civilization, GPS, satellite networks, internet data routing, financial trading systems, mobile communication grids, is synchronized to atomic time with a precision that makes even millisecond-level discrepancies operationally significant. When the planet speeds up, the system of time that holds the digital world together has to be adjusted. Leap seconds, which were introduced in 1972 to periodically insert an extra second into coordinated universal time to account for the Earth's gradual slowing, may now need to be replaced or reversed. For the first time in history, scientists are discussing the possibility of a negative leap second, a moment subtracted from time to account for a planet moving faster than expected, a moment taken away from time itself. If you got to wonder what kind of world bends the rules of the clock, If the idea of a planet accelerating its own spin without warning or obvious cause strikes you as the kind of thing that deserves more than a footnote in a scientific journal, then you are already asking the right question. And that question, followed honestly, leads somewhere much deeper than milliseconds. It leads into the interior of the Earth itself, into the churning iron sea at its core, into the invisible magnetic envelope that shields all life from the lethal wind of the cosmos, and into a set of interconnected transformations that, taken together, paint a picture of a planet in the middle of something we are only beginning to have the instruments to detect and nowhere near the understanding to fully explain. If this kind of exploration resonates with you, if standing at the edge of what we know and peering into what we don't is the kind of experience you seek, subscribe to this channel, leave a like, and stay with us. Because what follows is not a summary. It is a descent. The Earth has been rotating for 4.5 billion years. In that time, it has been struck by objects large enough to vaporize oceans, reshaped by the slow collision of continents, frozen nearly solid, and then thawed again by volcanic outgassing that rebuilt its atmosphere from scratch. It has survived all of it, not unchanged, never unchanged, but intact, spinning, persistent. The rotation itself is not new. What is new is our ability to measure it with a precision that reveals, for the first time, that this ancient, seemingly inexorable motion is not locked in place. It breathes, it fluctuates. It responds to forces that act on it from above, from below, and from within. Forces that interact in ways so complex, so deeply coupled across scales of space and time, that even now, with satellites and supercomputers and instruments sensitive enough to detect the footfall of a human being, our picture of why the Earth spins the way it does remains stubbornly incomplete. The planet is not a machine with fixed gears. It is a living system, dynamic, layered, constantly redistributing mass and momentum in response to its own internal evolution and to the gravitational conversations it carries on, perpetually with the moon, the sun, and the slow tide of cosmic forces that have shaped it since before the first molecule of what would eventually become life assembled itself in some ancient warm sea. The rotation you have never thought about is changing, and the reasons why reach all the way down to the center of the world. To understand what is happening, you first have to understand what the Earth actually is. Not the planet of the school textbook, that simple diagram of concentric shells, crust, mantle, outer core, inner core, each layer drawn with clean lines as if they were rooms in a building with well-defined walls and quiet interiors. That picture is not wrong exactly, but it is incomplete in the way that a map of a continent is incomplete. Technically accurate in outline, but utterly silent on the storms. The Earth is in motion all the way down. Stand somewhere still. Not still the way you are still when you sit quietly in a chair. Still in the sense of genuinely motionless, with no wind, no traffic, no ambient vibration from the world's machinery. Stand there, close your eyes, and try to feel the planet moving. You cannot. And that absence of sensation is itself one of the most profound illusions in human experience, because you are, at this moment, depending on where you stand on the surface of this planet, rotating through space at somewhere between 0 and approximately 1,670 kilometers per hour. At the equator, the full equatorial speed. At the poles, nearly nothing. The axis holds still while everything else sweeps around it. At a middle latitude, somewhere in between, you are being carried through the curve of Earth's rotation at a speed that, if you were suddenly detached from the planet's surface, would fling you outward like a stone released from a sling. The only reason you do not feel this is that the motion is perfectly, continuously transmitted through every atom of your body, through the air above you and the ground beneath you, through every object in your environment. There is no relative motion to perceive because everything is moving together. This is the first thing you have to truly absorb before the strangeness of what is happening becomes legible. You are living on a spinning sphere, not metaphorically, physically, measurably, consequentially. And the speed at which that sphere spins is not merely an astronomical curiosity. It is an engineering parameter on which the entire structure of modern life is built. Consider GPS. When you open a navigation application and it places you within a few meters of your actual location on the surface of the Earth, what is actually happening is a negotiation between your device and a constellation of satellites orbiting the planet at altitudes of roughly 20,000 kilometers. Those satellites carry atomic clocks. They transmit signals encoding precise timestamps and positional data. Your device receives multiple such signals, compares the arrival times, and uses the differences to triangulate your position. The accuracy of this system depends entirely on the accuracy of the time measurements, and because the satellites and your device are moving relative to each other, and because both are subject to gravitational and relativistic effects that alter the flow of time at measurable levels, the entire system must be continuously corrected against a universal reference. That reference is atomic time, the time that the Earth's rotation is supposed to define. When the Earth speeds up or slows down, when the length of a day deviates from its expected value, the correspondence between atomic time and rotational time drifts. For most of human history, this was not a problem, because our ability to measure the difference did not exist. Now it does, and maintaining the synchronization that modern infrastructure requires means accounting for every millisecond of deviation. The discrepancy is small, but the systems that depend on it are not forgiving of small errors. A single misaligned millisecond propagated through a GPS system can produce a positional error of roughly 30 centimeters. In aviation, in financial trading, in precision agriculture, in the coordination of data packets across global internet infrastructure, 30 centimeters is not nothing. But set aside the technological implications for a moment. They are real, but they are downstream of something far more profound. What matters first is understanding why the Earth's rotation changes at all. What physical mechanisms are capable of adding or removing milliseconds from a planet's day, because that understanding is the only lens through which the anomalies of recent years become genuinely legible. The Earth's rotation is governed by angular momentum, a quantity that, in a closed system with no external torques, is conserved. This is one of the most robust principles in physics. A spinning object will continue spinning at the same rate unless something acts upon it. For the Earth, the most significant external actor is the Moon, whose gravitational pull creates tidal bulges in the planet's oceans and crust, and whose interaction with those bulges exerts a gentle but relentless braking force on Earth's rotation. Over geological time, this tidal friction has been doing its work steadily. Roughly 1.4 billion years ago, a day on Earth lasted only about 18 hours. 400 million years ago, there were perhaps 400 days in a year. Today, 24 hours. In the far future, if the solar system persists long enough, the day will lengthen further, and eventually, over time scales that make human history look like a single breath, the Earth and Moon could become tidally locked, each showing only one face to the other, suspended in a permanent gravitational embrace. That slow, majestic deceleration, measured in milliseconds per century, is the expected, the predictable, the background story. It is the long exhale of angular momentum leaving the planet across deep time. What is not expected, what is not captured by the background story, are the short-term fluctuations. The jitters, the tremors in rotational speed that occur over months and years, that do not fit the smooth curve of tidal deceleration, that require explanation from mechanisms operating not across billions of years, but across human timescales. And here is where the picture becomes genuinely complicated, because the mechanisms that can change Earth's rotational speed in the short term are numerous, interconnected, and imperfectly understood, and because isolating the contribution of each one to the total observed variation is a problem that has occupied geophysicists for decades without complete resolution. Think of the planet as a figure skater. You have seen the image before, a skater with arms extended, spinning at a moderate pace, who then draws their arms inward and instantly accelerates into a blur of rotation. The physics is angular momentum conservation. As the mass of the arms moves closer to the axis of rotation, the moment of inertia decreases and the rotation rate increases to compensate. The total angular momentum of the system stays the same, only its distribution changes. The Earth operates by exactly the same principle. When mass moves toward the rotational axis, toward the poles, the planet speeds up. When mass moves away from the axis, toward the equator, it slows down. Any redistribution of mass on the planet's surface or in its interior has rotational consequences. Now hold that thought, that image of a skater, of mass in motion, of rotation responding, and consider what is happening to the surface of this planet right now. The polar ice sheets are melting, not slowly, not gradually in the way that geological processes typically unfold, but at a pace that is, by the standards of Earth history, startlingly rapid. Greenland alone is losing roughly 280 billion metric tons of ice per year. Antarctica is losing approximately 150 billion metric tons annually. That ice, that mass, is not disappearing. It is becoming water, flowing through rivers and streams, entering the oceans, and redistributing itself across the planet's surface. When ice that was sitting near the poles, near the rotational axis, becomes water that spreads toward the equator, the moment of inertia of the planet increases. The skater extends her arms. The planet should slow down, and yet, the planet has been speeding up. This is the contradiction that keeps geophysicists awake at night. The surface redistribution of mass from polar melting should, by the physics of angular momentum conservation, be causing the Earth to rotate more slowly. The fact that it has been doing the opposite, that the measured length of the day has in recent years been trending shorter rather than longer, means that some other mechanism, or combination of mechanisms, is overriding the expected effect. Something is moving mass inward, toward the axis, or otherwise acting on the planet's rotation in a way that outpaces and reverses the deceleration that the climate crisis alone would predict. Something deeper, something we cannot see from the surface, cannot photograph from satellites, cannot sample with ocean buoys or atmospheric sensors. Something happening in the interior. And the interior of the Earth is where the real story lives, a story that begins not in the geophysics departments of universities, not in the satellite operations centers where GPS engineers fret over millisecond discrepancies, but 6,300 kilometers below the ground beneath your feet, in a place of pressures and temperatures so extreme that matter itself behaves in ways that have no parallel in ordinary human experience. A place where iron flows like water and water cannot exist. A place that has never been directly observed, never been sampled, never been visited by any instrument built by human hands. And yet a place whose behavior shapes everything that happens on the surface of this world, including the length of every day you will ever live. There is a place at the center of the Earth where the pressure is so extreme that it exceeds 3.5 million times the atmospheric pressure you feel on your skin right now. Where the temperature reaches somewhere between 5,000 and 7,000 degrees Celsius, comparable to the surface of the sun. Where iron, which you know as a hard, brittle metal that rusts in humid air, exists as a solid sphere, not because it is cold enough to be solid, but because the pressure squeezing it from every direction is so immense that it has no choice. Iron forced into solidity, not by cold, but by weight. By the crushing mass of an entire planet pressing inward from all sides simultaneously. This is the inner core. A sphere of solid iron and nickel approximately 2,400 kilometers in diameter, roughly the size of the moon, suspended at the geometric center of the Earth, surrounded by a sea of liquid iron that churns and flows around it in slow, majestic, convective currents that have been running, uninterrupted, for billions of years. You will never see it. No human instrument has ever penetrated to it. No drill has come within even a small fraction of the distance required to reach it. The deepest borehole ever drilled, the Kola Superdeep borehole in Russia, reached approximately 12 kilometers before the heat and pressure defeated the machinery, and 12 kilometers is to 6,300 kilometers what the thickness of a piece of paper is to the height of a 10-story building. We know the inner core exists not because we have seen it, but because the Earth itself has shown it to us, through sound. Through the seismic waves generated by earthquakes, which travel through the planet's interior, the way sound waves travel through a body of water, bending and reflecting and changing speed as they pass through materials of different densities and states. Seismologists read these waves the way a radiologist reads an X-ray. translating the patterns of arrival times and wave shapes at monitoring stations distributed around the globe into a picture of the planet's interior structure. It is indirect knowledge, inference by vibration, but it is extraordinarily precise. Precise enough to reveal not just the existence of the inner core, but something about how it moves. And here is where the story takes a turn that even specialists describe with a particular kind of quiet astonishment. The inner core rotates, independently. The rest of the planet turns around it, and it turns at its own rate, slightly faster than the mantle and crust above it, or so scientists believed for decades after the phenomenon was first proposed in 1996 by seismologists Xiaodong Song and Paul Richards, who analyzed seismic wave travel times and found subtle differences consistent with a core that was outrunning the rest of the planet by roughly 1 degree of longitude per year. 1 degree. A small number, but an extraordinary one. It meant the solid iron heart of the Earth was lapping the surface like a runner slightly faster than the track they share, completing an extra full rotation relative to the mantle approximately every several centuries. This was already remarkable. The existence of differential rotation inside a planet, layers moving at different speeds, decoupled from each other by the liquid iron buffer of the outer core, which transmits angular momentum but does not rigidly lock the inner core to the mantle. This was a discovery that changed how geophysicists thought about planetary interiors. It meant the Earth's center was not just sitting there, passive, a fixed point around which everything else revolved. It was participating. It was a dynamic actor in the planet's rotational system, with its own momentum, its own behavior, responding to forces that acted on it from the liquid core surrounding it, electromagnetic forces generated by the geodynamo, gravitational forces from the mantle above, and in turn influencing the behavior of those systems through the coupling between them. But recently, the story has grown stranger still. In 2023, a study published in the journal Nature Geoscience by Yi Yang and Xiaodong Song, the same Song who had first identified differential rotation nearly 3 decades earlier, presented new seismic evidence suggesting that the inner core had, around 2009, slowed its prograde rotation relative to the mantle and may have stopped, may have paused in place, and then the detail that landed in the scientific community with the weight of something genuinely unprecedented may have begun rotating in the opposite direction. Retrograde. The solid iron center of the Earth, which for decades we believed was steadily outpacing the surface, appearing to reverse, to turn back. The reaction from other geophysicists was not uniform. Science rarely moves as a single body. Other research groups, using different seismic datasets and different analytical methods, reached different conclusions, some arguing that the apparent reversal was an artifact of how the data was interpreted, others proposing that the inner core's rotation was oscillating on a timescale of several decades, swinging back and forth like a pendulum in slow motion, with the recent behavior representing one phase of a longer cycle, rather than an unprecedented departure from normal. The debate is ongoing, unresolved, vivid. But the existence of the debate itself is telling, because what everyone agrees on is that the inner core is doing something, that its rotational behavior has changed in ways that are detectable in the seismic record, that the neat, steady picture of a core perpetually and predictably outrunning the rest of the planet no longer fits all the available data. What does it mean for a planet's rotation when the solid sphere at its center changes speed? The answer is not simple, and it is not fully known, but the physical reasoning is clear enough to be sobering. The inner core and the mantle are coupled, not rigidly, not the way 2 gears are coupled by interlocking teeth, but electromagnetically and gravitationally, through interactions that are diffuse and distributed but real. When the inner core accelerates, it pulls on the mantle above it, however subtly. When it decelerates, it gives back angular momentum to the mantle. The exchanges are not instantaneous. They propagate through the liquid outer core over timescales of years to decades, but they are measurable. And the variations in Earth's rotation rate that atomic clocks have been registering, the millisecond scale fluctuations that do not fit the smooth curve of tidal deceleration, show correlations with the known behavior of the deep interior that are too consistent to be coincidental. Something is happening between the core and the surface. a dialogue conducted in angular momentum, transmitted through thousands of kilometers of liquid iron and solid rock, playing out across decades, and expressing itself at the top of the system as a day that is slightly longer or slightly shorter than it should be, as a millisecond added or subtracted, as a clock that must be adjusted to stay synchronized with a planet that is, in ways no one fully predicted, renegotiating the terms of its own rotation. But the deep interior is only one part of the system. The surface, too, is in motion. The atmosphere is in motion. The oceans are in motion. And all of these moving masses are participants in the same angular momentum budget that governs the length of the day, each contributing their share, each capable of shifting the balance in directions that amplify or cancel the effects of the others. To understand the full picture, you have to hold all of these systems in mind simultaneously, a feat that taxes even the most sophisticated computational models, and that reveals, at its edges, the true extent of what we do not yet know. The skater is not alone on the ice. The ice itself is melting. The air above her is churning. And somewhere below the rink, something immense and slow and iron-heavy has just changed direction. Here is the paradox that sits at the center of everything. We are living through the most technologically sophisticated era of Earth observation in the history of science. Hundreds of satellites orbit the planet continuously, measuring gravity anomalies, ice thickness, sea level, atmospheric density, and crustal deformation with a precision that would have seemed fantastical to scientists of even 50 years ago. The Global Navigation Satellite System tracks the position of any point on Earth's surface to within millimeters. The Gravity Recovery and Climate Experiment, GRACE, detects changes in Earth's gravitational field by measuring the distance between two satellites flying in formation, a distance that varies by as little as a micron in response to mass redistribution on and inside the planet below. A micron, 1/1,000,000th of a meter. We are watching this planet with instruments of almost incomprehensible delicacy, and yet we cannot agree on why the Earth is spinning faster. This is not a failure of instruments. The instruments are extraordinary. This is something deeper, a failure, or more precisely a limit, of models, a gap between what we can measure and what we can explain, and in that gap lives the most uncomfortable truth in contemporary geophysics. Our picture of Earth's interior, assembled from indirect inference over more than a century of seismology, is still so incomplete that it cannot account for the behavior we are observing. We are, in a precise and unsettling sense, watching a system we do not fully understand undergo changes we did not fully predict. Let us be exact about what the data shows and where the explanation breaks down. The length of Earth's day fluctuates on multiple timescales. There are seasonal variations. The atmosphere shifts mass around as weather patterns change, and the oceans redistribute water in response to temperature and wind. These variations are well characterized and can be modeled reasonably well. There are interannual variations linked to phenomena like El Niño, which redistributes enormous masses of warm water across the Pacific and measurably affects Earth's rotation. These, too, are understood at a level sufficient for prediction. And then there are the longer period variations, fluctuations on timescales of decades, that correlate with changes in the deep interior, with the behavior of the liquid outer core, with the slowly varying electromagnetic coupling between core and mantle. These are understood in outline but poorly constrained in detail. What is not well understood is the combination. The way seasonal effects interact with deep interior effects. The way a change in inner core rotation propagates through the liquid outer core over years and then emerges at the surface as a perturbation in rotation rate precisely at the moment when surface processes are also operating in the same direction. The way the atmosphere, the oceans, the cryosphere, the mantle, the outer core, and the inner core, 6 distinct dynamical systems, each with its own characteristic timescales and physical laws, are coupled to each other through exchanges of angular momentum that occur continuously, simultaneously, and at every scale from milliseconds to millions of years. To model this system completely would require a computational representation of every kilogram of water in the global ocean, every kilogram of ice in every glacier, every parcel of air in the global atmosphere, every convective current in the liquid iron outer core, and every process by which these systems exchange momentum with each other. That model does not exist. It cannot exist, given current computational resources. What exists instead are partial models. Excellent partial models, in many cases, but partial nonetheless, and the regions where the partial models meet, where the atmospheric model hands off to the ocean model which connects to the mantle model which feeds into the core model, are precisely the regions where the greatest uncertainty lives. The problem is even more fundamental than computational power, however. Some of what we do not know about Earth's interior is not a matter of insufficient processing speed. It is a matter of insufficient observational constraint. The seismic wave data from which we construct images of the deep interior is dense in some regions of the planet and sparse in others. We have far more seismic monitoring stations in North America and Europe than in the ocean floors, which cover more than 70% of Earth's surface. Our picture of the deep interior is therefore systematically biased by the geography of our observation network, like trying to understand the weather of an entire continent by only reading thermometers placed in a few cities. The map we have drawn of Earth's interior has regions of high confidence and regions of profound shadow. And the inner core, that solid iron sphere at the center of everything, is the most shadowed region of all. We know it is there. We know it is iron-nickel, solid, roughly lunar in size. We know it rotates differentially. We do not know precisely how fast, in which direction relative to the mantle at any given time, how the rotation has varied over centuries or millennia for which we have no seismic records, how its surface, if you can call the boundary between solid and liquid iron a surface, exchanges momentum with the liquid outer core above it, or how the complex crystalline structure of the solid iron at such extreme pressures and temperatures affects the way seismic waves pass through it, and therefore affects our ability to interpret those waves correctly. There is a further complication, one that rarely surfaces in popular accounts of this subject, but that specialists consider particularly important. The inner core may not be uniform. Recent seismic studies suggest it has internal structure, hemispheric differences in wave propagation speed that hint at anisotropy, at iron crystals aligned in different orientations in different parts of the core, possibly as a record of its complex formation history. There are even proposals of an inner core, a distinct innermost region with properties different from the outer portions of the inner core surrounding it. If this is true, then the object whose rotation we are trying to characterize is not a simple homogeneous sphere, but a layered, asymmetric, structurally complex body. And the rotation of one part of it may not be the same as the rotation of another. We are, in other words, arguing about the behavior of something we have never seen, using data collected by instruments that can only infer its properties indirectly, interpreted through models that disagree with each other on fundamental points. This is not science failing. This is science working at its frontier, which is always uncomfortable, always contested, always populated by uncertainties that are not rhetorical performances, but genuine epistemic conditions. The frontier is the place where the questions are real and the answers are not yet. And the frontier of Earth rotation science is a place of extraordinary richness right now. Because the data is better than it has ever been, the questions are sharper than they have ever been, and the gap between them, that fertile, disturbing gap, is more visible than it has ever been. But the real weight of this paradox is not scientific, it is existential. The length of the day is not an abstraction. It is not a number that matters only to atomic physicists and GPS engineers. It is the most fundamental unit of time that life on this planet has ever known. Every circadian rhythm in every living organism on Earth, from the cyanobacteria that were keeping biological time billions of years before animals existed, to the neurons in your brain that regulate your sleep and wakefulness and mood and metabolism, is calibrated to the 24-hour cycle of light and dark that Earth's rotation produces. That calibration is not superficial. It is written into DNA. It is structural. Circadian clocks in living cells are molecular mechanisms that evolved over billions of years of selection pressure imposed by the rotation of this planet. When the rotation changes, even by fractions of milliseconds, the light-dark cycle does not change in any way biology can register. The changes are too small, too slow. But they are symptoms, Symptoms of a system in motion, a system whose behavior at the deepest levels we are only beginning to read. And symptoms have a way, in complex systems, of being the first legible signs of processes whose full expression comes much later. The question is not whether the Earth is changing. It is. The question is what kind of change this is. Whether these fluctuations in rotation are noise within a stable long-term trend, or whether they are the early legible chapters of something larger. Something that operates on timescales our civilization has never had to navigate. Something that the planet has done before, many times, without us here to notice. Something like what is happening to the magnetic field. Imagine you are standing outside at night, somewhere far from city lights, and you look up at a sky dense with stars. The light reaching your eyes has traveled for years, decades, centuries, some of it for millions of years, crossing an emptiness that is not truly empty. Space, the space between stars, between planets, between you and the faint smear of the Milky Way above you, is threaded with radiation. Charged particles flung outward by stellar winds. High-energy protons and electrons accelerated to near light speed by the shock waves of distant supernova explosions. Cosmic rays, a misleading name because they are not rays of light but streams of atomic nuclei, some of them carrying energy so extreme that when they strike the upper atmosphere, they generate cascades of secondary particles that can be detected at ground level. This radiation is constant, omnidirectional, and lethal in sufficient doses. It is one of the fundamental hazards of existing in a universe that runs on nuclear physics. You are alive. The organisms around you are alive. The biosphere of this planet has been alive for approximately 3.5 billion years. And for all of that time, life on Earth has been bathed in this radiation and survived it. Not by developing cellular machinery capable of withstanding unlimited particle bombardment, because no such machinery is possible, but because the Earth itself provides a shield. A shield generated not by rock or water or atmosphere alone, but by something far more elegant, far more improbable, and far more consequential than any physical barrier. A magnetic field produced by the flowing liquid iron of the outer core, shaped by the planet's rotation into a structure that extends tens of thousands of kilometers into space and deflects the vast majority of the charged particle flux before it can reach the surface. The magnetosphere, the invisible armor of the living planet. To understand how it is generated, you need to hold in mind a process called the geodynamo, one of the most complex, naturally occurring physical phenomena known to science. The outer core is a shell of liquid iron roughly 2,200 kilometers thick, surrounding the solid inner core, itself surrounded by the rocky silicate mantle. This liquid iron is a conductor of electricity. It is also in constant motion, driven by heat flowing outward from the inner core, by compositional buoyancy as the inner core slowly grows and releases lighter elements into the liquid above it, and by the Coriolis effect of Earth's rotation, which organizes the convective flows into patterns aligned preferentially with the rotational axis. When a conducting fluid moves through a magnetic field, it generates electric currents. When electric currents flow through a conducting fluid, they generate magnetic fields. The fields reinforce the currents that created them, the currents sustain the fields, and the whole system bootstraps itself into a self-sustaining dynamo, a planetary-scale electromagnetic engine that has been running continuously for at least 3.5 billion years. The output of this engine is the geomagnetic field. At Earth's surface, it is relatively weak, roughly 100 times weaker than the field of an ordinary refrigerator magnet, but it extends far into space, where its interaction with the solar wind creates the magnetosphere, a teardrop-shaped cavity in the plasma flowing out from the sun, compressed on the sunward side to perhaps 60,000 kilometers, and stretched on the night side into a magnetotail that extends for millions of kilometers. Charged particles from the sun and from cosmic sources enter the magnetosphere, but are mostly deflected, guided by field lines toward the polar regions, where they spiral down into the upper atmosphere and produce the auroras. The middle latitudes, where the vast majority of complex life exists, are largely shielded. The field is not impenetrable. Some radiation gets through, always has, but without it, the surface flux of energetically damaging particles would be orders of magnitude higher. the atmosphere itself would be more vulnerable to erosion by the solar wind, as Mars, which lost its magnetic field billions of years ago, dramatically demonstrates. The field is not static. It fluctuates in intensity, it shifts in direction, and the positions of the magnetic poles wander continuously, sometimes slowly, sometimes at speeds that seem, by geological standards, startlingly rapid. For most of recorded human history, this wandering was too slow to be noticeable over a human lifetime. The compass pointed roughly north, with modest variation depending on location and era. Navigators learned to account for magnetic declination, the angular difference between magnetic north and geographic north, and adjusted their charts accordingly. The field seemed reliable, permanent in the way that the stars seemed permanent. Background. Then, around the beginning of the 20th century, scientists began to assemble a picture of the geomagnetic field's past behavior from an unlikely archive, the rock record. When magma solidifies into rock, the magnetic minerals in the cooling material align themselves with the ambient magnetic field at the moment of crystallization, preserving a record of the field's direction and intensity at that time. This paleomagnetic record, extracted from thousands of rock formations around the world and spanning hundreds of millions of years, revealed something that no one in the era of compass navigation had suspected. The magnetic field reverses completely. Periodically, on timescales ranging from tens of thousands to millions of years, the north magnetic pole becomes the south magnetic pole and vice versa. The field does not flip instantaneously. The transition takes thousands of years, a geological eye blink, but a span of time vastly longer than any human civilization. During this transition, the field weakens dramatically, becomes highly irregular, loses its organized dipolar structure, and for a period leaves the planet with only a fraction of its normal magnetic shielding. This has happened hundreds of times. The last complete reversal, the Matuyama-Bruni's reversal, occurred approximately 780,000 years ago. Modern humans did not exist. Our ancestors, early members of the genus Homo, were present, along with the entire Pleistocene megafauna, and life continued through the reversal without a mass extinction. But the biosphere of 780,000 years ago was not technologically dependent on satellite navigation and electromagnetic infrastructure. And the radiation environment during a reversal, while not apocalyptic, is genuinely more challenging than what life currently experiences under a full-strength field. Now hold those facts alongside this one. The geomagnetic field is currently weakening, not at the leisurely pace of its average long-term behavior, but at a rate that has accelerated measurably over the past 2 centuries of systematic magnetic observation. The field has lost approximately 9% of its strength since measurement began in the 1840s. The South Atlantic anomaly, a region centered roughly over South America and the South Atlantic Ocean, where the field is anomalously weak, allowing charged particles to dip closer to the surface than they do elsewhere, has been expanding and deepening. Satellites passing through it experience elevated rates of electronic malfunction due to increased particle radiation. The region is large enough that commercial aircraft operating at altitude through it receive measurably higher radiation doses than flights at comparable altitudes elsewhere. The North Magnetic Pole, which for most of the past several centuries wandered through the Canadian Arctic at speeds of a few kilometers per year, began accelerating in the late 20th century. By the early 21st century, it was moving at roughly 50 to 60 kilometers per year, fast enough that the World Magnetic Model, the international reference system used by navigation and mapping systems worldwide, had to be updated ahead of its normal 5-year revision schedule for the first time in its history. The pole is now traversing the Arctic Ocean, heading towards Siberia, at a pace that geophysicists describe as unusual within the context of the historical record. Is this the beginning of a reversal? Or is it an excursion? A temporary large departure from the average field direction that eventually recovers without completing a full polarity flip? Or is it simply a fluctuation within the normal range of geomagnetic variability, the kind of thing that has happened many times in the past without dramatic consequence? The honest answer is that no one knows with certainty. What is known is that the patterns currently observed, weakening intensity, accelerating pole migration, expanding anomaly regions, are consistent with what the paleomagnetic record shows in the periods leading up to past reversals and excursions. They are also consistent with fluctuations that did not lead to reversals. The data is genuinely ambiguous at this stage, and anyone who claims certainty in either direction is overstating what the science currently supports. What is not ambiguous is the connection between the field's behavior and the dynamics of the outer core, the same liquid iron system that drives the geodynamo, that couples electromagnetically to the inner core, that participates in the angular momentum exchanges that express themselves at the surface as variations in the length of the day. The weakening of the field, the migration of the poles, the expansion of the South Atlantic anomaly, all of these are signatures of changes in the flow patterns within the outer core, changes in how the liquid iron is moving, changes in the structure of the convective currents that sustain the dynamo, and those changes in core flow are connected, through the same electromagnetic and gravitational coupling mechanisms, to the behavior of the inner core, whose anomalous rotation has occupied scientists for the past several years. Everything is connected: the rotation and the field, the inner core and the outer core, the core and the mantle, the deep interior and the surface, the length of the day and the strength of the shield that makes the surface habitable. These are not separate phenomena that happen to be changing simultaneously by coincidence. They are expressions, at different levels of the system, of a single underlying reality. The interior of the Earth is in a state of dynamical change, and the surface, the thin, fragile, inhabited skin of this planet, is beginning to register that change in ways our instruments can now measure, even if our understanding of its full implications remains incomplete. The machine beneath our feet is not broken, but it is unmistakably rearranging itself. Every answer in a system this complex opens onto a larger question. Every mechanism identified reveals another mechanism behind it. Every layer peeled back exposes a deeper layer whose properties are less well known, whose behavior is harder to predict, and whose consequences, if it changes, are harder to bound. This is not a characteristic of bad science. It is the characteristic of a real system, a system whose complexity is not a deficiency of our models, but a property of the thing itself. And as the layers accumulate, as the picture of Earth's interior dynamics grows richer and more intricate, what emerges is not comfort, but a particular kind of productive vertigo. The feeling of understanding something well enough to see how much remains to be understood. Consider the mantle, not the outer core, not the inner core. The mantle, that vast shell of solid but slowly deforming silicate rock that occupies the space between the core mantle boundary at roughly 2,900 kilometers depth and the base of the crust a few tens of kilometers below your feet. The mantle is solid the way glass is solid. On human timescales, it behaves like rock. On geological timescales, it flows like an extraordinarily viscous fluid. It convects. Hot material rises from near the core mantle boundary over millions of years, spreads laterally as it approaches the surface, cools, and sinks back down. This is the engine of plate tectonics, the slow churning of mantle convection that pushes the tectonic plates across the surface, opens ocean basins, builds mountain ranges, and drives volcanic activity. A process so slow that human civilization has existed for only the tiniest fraction of a single convective cycle. At the boundary between the outer core and the core-mantle boundary, something remarkable and poorly understood happens. The two most dynamic fluid systems in the planet meet. Hot liquid iron from below encounters hot solid silicate from above. The exchange of heat across this boundary drives the buoyancy that sustains mantle convection. But the boundary is not smooth, not featureless. There are structures there. Anomalously slow seismic regions nicknamed Large Low Shear Velocity Provinces, or LLSVPs, two continent-sized masses of material that appear to be compositionally distinct from the surrounding mantle, sitting at the base of the mantle beneath Africa and beneath the Pacific Ocean, and have been sitting there, apparently stable, for hundreds of millions of years or more. There are ultra-low velocity zones, patches where seismic waves slow to a crawl, that may represent partial melting at the base of the mantle, or compositionally exotic materials, or both. There is complexity that our current imaging cannot fully resolve. And then there are the plumes, columns of unusually hot mantle material that rise from near the core mantle boundary, narrow and fast-moving by mantle standards, punching through the overlying rock like blowtorches through wax and reaching the surface as hotspots. The volcanic chains of Hawaii, Iceland, Yellowstone, the Canary Islands. These plumes are thought to originate from near the thermal boundary layer at the base of the mantle, possibly from the edges of the LLSVPs. They are long-lived, but they are not static. They pulse, they wobble, and when a plume reaches the surface and feeds a supervolcano, a volcanic system of the kind that has, multiple times in Earth history, erupted enough material to alter the global climate for years or decades, the consequences extend far beyond geology. Now layer onto this the tectonic system itself. The plates are moving, have always been moving, but the distribution of mass across Earth's surface changes as they move, and mass distribution affects rotation. Great earthquakes, which occur along plate boundaries and in subduction zones where one plate dives beneath another, redistribute crustal mass instantaneously on geological timescales. The 2004 Sumatra earthquake, magnitude 9.1, the third largest ever recorded, was estimated to have shortened the length of the day by approximately 2.68 microseconds by redistributing mass toward the planet's rotational axis. Microseconds, not milliseconds, even smaller. But the principle is the same, and large earthquakes occur regularly on geological timescales, accumulating their rotational effects over millions of years. The 2011 Tohoku earthquake in Japan similarly shortened the day by a smaller amount and shifted Earth's rotational axis by several centimeters. When you begin to enumerate all of these systems, the tides from the moon, the redistribution of meltwater from glaciers, the atmospheric angular momentum cycles driven by weather, the oceanic angular momentum cycles driven by currents, the mantle convection driven by core heat, the electromagnetic coupling between the outer core and the inner core, the gravitational coupling between the inner core and the mantle, the periodic perturbations from major earthquakes, and when you try to account for all of them simultaneously in a single model that must reproduce the observed millisecond scale variations in the length of the day, you are confronted with the full scope of the problem. It is not a problem with a clean solution waiting to be found. It is a problem in complex system science, where the interactions between components produce emergent behaviors that cannot be predicted from the properties of any individual component, and where the sensitivity to initial conditions is high enough that small uncertainties in the interior state of the planet propagate into large uncertainties in future behavior. But perhaps the most troubling complication, the one that sits outside the already complex inventory of geophysical mechanisms, is the one being actively introduced by the species doing the measuring. Human civilization has, in the span of roughly 2 centuries, become a geophysical force. Not metaphorically, measurably. The redistribution of mass caused by the extraction of groundwater from deep aquifers, pumping water that has been stored underground for millennia and releasing it into the hydrological cycle, ultimately depositing it in the oceans, has measurably affected Earth's rotation and the position of its rotational axis. A 2023 study published in Geophysical Research Letters calculated that between 1993 and 2010, the redistribution of groundwater caused by human extraction shifted Earth's rotational pole by approximately 80 centimeters, primarily eastward, 80 centimeters, caused by pumping water. The authors described it as the dominant contributor to polar wander during that period, outpacing all other individual factors studied. Let that settle for a moment. The physical location of the axis around which this planet rotates has been shifted by human activity, not by nuclear weapons, not by asteroid impact, by irrigation. Meanwhile, the melting of polar ice, driven by the warming of the atmosphere caused by the emission of greenhouse gases produced by the combustion of fossil fuels, is also affecting polar wander and rotation rate, as described earlier. The two effects are not independent. Climate change accelerates glacial melting, which shifts polar ice mass to the oceans, which shifts the rotational axis and changes the rotation rate. and the rate of change of these effects is accelerating as emissions continue and global temperatures rise. We are, therefore, not merely observing a planet whose rotation is changing. We are participating in that change, introducing perturbations into a system whose behavior we do not fully understand, whose response functions on long timescales we cannot reliably compute, and whose current state of change at the deep interior level is already poorly characterized. We are adding noise to a signal we are still learning to read, and the signal itself is trying to tell us something, not in words, not in any language that was ever designed for human comprehension, but in the accumulated data of atomic clocks and GPS satellites, in the wobble of the rotational axis measured by very long baseline interferometry, in the subtle variations in gravitational field strength recorded by the GRACE satellites, in the seismic waves that pass through the iron interior of the planet and arrive at monitoring stations slightly earlier or slightly later than expected. In all of this, the Earth is broadcasting, continuously, about what it is doing, about what is happening in the places we cannot reach or see. The question is whether we are listening carefully enough and whether we have built the conceptual frameworks to understand what we hear, because somewhere in the deep interior, something is changing direction. And what that means for the surface, for the field, for the rotation, for the climate of the next 10,000 years, is a question whose answer is still being assembled, piece by piece, from the most indirect evidence imaginable, by scientists who are doing something genuinely heroic, trying to understand the inside of a planet from the outside, one trembling seismic wave at a time. There is a thought experiment that geophysicists sometimes use when they want to convey the true strangeness of the system they study. Imagine that you could freeze the Earth, not in temperature, but in time. Stop everything. Halt the rotation, the convection, the tidal pull of the moon, the flow of the liquid outer core, the slow creep of tectonic plates. Hold every atom of every system perfectly still, suspended in a single instant, and then ask, what would happen next if you released it? The answer is not that everything would simply resume where it left off. The answer is that the system would immediately begin reorganizing, catastrophically in some cases, because the frozen state is not an equilibrium state. It is a snapshot of a process. Remove the process, and the snapshot has no meaning. The Earth is not a collection of objects sitting in space. It is a collection of processes in perpetual interaction, each one dependent on the others, each one both cause and consequence within a web of feedback so intricate that no complete map of it has ever been drawn or ever could be. This is why the consequences of what is currently happening, the rotational fluctuations, the weakening and migration of the magnetic field, the possible reversal of the inner core's differential rotation, the human-driven redistribution of mass at the surface, cannot be neatly bounded, cannot be listed as a clean inventory of effects, because the effects are themselves processes, and processes interact, and the interactions produce outcomes that were not contained in any of the individual inputs. Complex systems do not sum. They compose. And what they compose is often something that none of their components, studied in isolation, would have suggested was possible. Begin with biology. Life on Earth is not merely coexisting with the geomagnetic field. It evolved inside it, with it, in continuous electromagnetic dialogue with it. The evidence for biological magnetoreception, the ability of organisms to sense and use the geomagnetic field for orientation, is now overwhelming. Migratory birds use it. Sea turtles use it to navigate across entire ocean basins and return, decades later, to the exact beach where they hatched, guided at least in part by a magnetic map encoded in their nervous systems. Sharks and rays sense it. Bees use it. Bacteria, magnetotactic bacteria, synthesize chains of magnetite crystals inside their cells and orient themselves along field lines. Even humans may have vestigial magnetoreceptive capacity. Magnetite crystals have been found in human brain tissue, though their functional significance remains debated. If the field weakens substantially, or if its structure becomes highly irregular during a transition period, what happens to systems that depend on it for navigation and orientation? The honest answer is that we do not know, because we have never observed a field reversal in the presence of a biosphere, anything like the current one. The last full reversal was 780,000 years ago. The fossil record around that time does not show a global mass extinction, but it shows local extinctions. It shows changes in species distributions. It shows the kinds of ecological reorganizations that leave marks in the sedimentary record, but are difficult to fully interpret across such a span of time. The absence of a dramatic extinction signal is genuinely reassuring. It is not the same as the absence of biological consequence. For modern civilization, the consequences of a weakening or reversing field are more legible, because modern civilization is electromagnetic in a way that no previous biosphere has ever been. The entire infrastructure of the digital age, satellite communications, GPS, electrical power grids, the internet, is sensitive to variations in the space weather environment that the magnetosphere mediates. When the field is strong and well organized, the magnetosphere efficiently deflects the charged particles of the solar wind. When the field is weak or disorganized, more particles penetrate. Energetic solar events, coronal mass ejections, which periodically fling billions of tons of magnetized plasma toward Earth at speeds of millions of kilometers per hour, interact with a weakened magnetosphere differently than with a strong one. The induced electrical currents that large geomagnetic storms produce in long conducting structures, power lines, pipelines, undersea cables, are larger when the external field is weaker. The 1989 geomagnetic storm that collapsed the entire power grid of Quebec in 90 seconds, leaving 6 million people without electricity, occurred during a period of normal field strength. During a period of significantly reduced field strength, comparable storm-induced events could be substantially more severe. Then there is the atmospheric dimension. The magnetosphere does not just deflect charged particles. It deflects cosmic rays, high-energy particles from outside the solar system. And cosmic rays, when they penetrate the upper atmosphere, can influence cloud formation by ionizing air molecules that serve as condensation nuclei. This mechanism, called the cosmic ray cloud connection, remains scientifically controversial. The quantitative significance of the effect is disputed. But if it is real, then a weakened field, by allowing more cosmic rays to reach the upper atmosphere, could subtly influence global cloud cover and therefore climate. The magnitude of the effect, if any, is poorly constrained. But the possibility adds another coupling to an already densely coupled system. Magnetic field strength and atmospheric optics and global temperature, all connected through a pathway that runs from the outer core to the edge of space and back down to the water droplets in a cloud. And then there is time. Not geophysical time, human time. The time of civilization, of recorded history, of technological development, of the accumulation of the infrastructure and knowledge and institutional continuity that makes modern life possible. The deepest challenge posed by what is happening to Earth's rotation and magnetic field is not technical, it is temporal. The processes involved operate on timescales that dwarf the entire span of human civilization. The inner core's oscillation cycle, if that is what it is, may span several decades to centuries. A full magnetic field reversal, if one is underway, would take thousands of years to complete. Tidal deceleration of Earth's rotation operates over millions of years. These are timescales on which human institutions, human knowledge systems, human governments, and human economies do not plan. Cannot plan, given the structures we have built. We have created a civilization of extraordinary technological sophistication, whose entire operating infrastructure sits atop geophysical systems that change on timescales our civilization has never been designed to think about. GPS was designed to be accurate today, and next year, and in a decade. It was not designed around the possibility that Earth's magnetic field might weaken by 30% over the next several centuries and require fundamental rethinking of the space weather protection assumptions embedded in the system's architecture. The power grid was designed around the historical frequency and intensity of geomagnetic storms under a field of current strength. It was not designed around a field half as strong, allowing twice the induced current from a comparable storm. This is the specific and sobering version of a much older human problem. We build for the conditions we know, and the conditions change. Every civilization in history has been built on assumptions about the stability of the environment that turned out, eventually, to be conditional rather than absolute. The ancient cities of the Indus Valley were built on assumptions about river systems that then changed. The agricultural civilizations of the Fertile Crescent were built on assumptions about rainfall patterns that then shifted. And contemporary technological civilization is built, in ways we rarely make explicit, on assumptions about the geomagnetic field, about the rotational stability of the planet, about the predictability of the space weather environment. Assumptions that are currently being tested by a set of geophysical changes that are real, measurable, ongoing, and imperfectly understood. The most important consequence of everything described in this account may not be the geophysical change itself, but the cognitive challenge it represents. The challenge of holding in mind, simultaneously, processes that operate across scales from milliseconds to millions of years. Systems whose components are coupled across the full depth of the planet. Uncertainties that are not rhetorical but genuine, and time horizons so far beyond the human lifespan that planning for them requires a relationship to the future that no civilization has yet fully developed. We have instruments precise enough to detect the rotation of the Earth's inner core. We have satellites that measure the changing gravitational field of the planet to micrometer precision. We have seismic networks that hear the planet's interior vibrating with the echoes of earthquakes. We have, in short, built the capacity to perceive what is happening. What we have not yet built, not fully, not with the urgency the situation deserves, is the capacity to respond to it across the timescales on which it matters. That is not a scientific failure. It is a civilizational one. And recognizing it is the first step towards something different, something harder and more necessary than measurement. Something that begins not in a laboratory, but in the way we think about where we are, what we are standing on, and how long it has been here, doing this, without us. There is a particular quality to the knowledge that the ground beneath you is moving, not the intellectual acknowledgement of it. We all carry that abstractly, as a fact absorbed in school and never truly felt, but the visceral, settled understanding of it. The understanding that arrives not as information but as a shift in how you inhabit the world. When it comes, it does not produce panic. It produces something closer to humility, a reorientation, a quiet recalibration of what it means to stand somewhere, to call something home, to speak of permanence. The Earth has been rotating for 4.5 billion years. In that time, it has survived impacts by objects large enough to vaporize entire oceans. It has been nearly completely glaciated, a snowball, white and silent, reflecting sunlight back into space as if in defiance of the star it orbits. It has experienced volcanic episodes so vast that the basalt flows covered areas the size of continents, and the gases released reshaped the atmosphere for millions of years. It has reversed its magnetic poles hundreds of times, each time passing through a period of disorder and weakness, and then reorganizing, reassembling the invisible architecture of its field from the turbulent currents of its iron heart. It has, in all of this, continued to turn, continued to generate the conditions for complexity, continued to be, against every probabilistic expectation, a planet on which extraordinarily intricate and fragile configurations of matter could not only exist but persist and compound over billions of years into the specific and improbable arrangement that eventually looked up at the night sky and wondered what was out there. We are that arrangement. We are, so far as we know, the only part of this planet that has ever asked a question about it. And the question we have been following through these pages: why is the Earth's rotation changing? What is happening in its interior? What does it mean for the field, for the surface, for us? Is not ultimately a question about geophysics. It is a question about our relationship to the system that produced us, about what it means to be conscious inside a process so vast and so ancient that consciousness itself is a negligible recent addition, a thin film of awareness on the surface of something that was already unimaginably complex before the first neuron ever fired. Here is what the science, taken as a whole, is telling us. The Earth is not a stable background against which human history takes place. It is a dynamic, layered, evolving system whose behavior on timescales longer than recorded history is characterized by change, by periods of relative stability punctuated by transitions, by the slow accumulation of stress and the eventual reorganization that releases it, by the perpetual redistribution of mass and energy and momentum across systems that are coupled in ways that defy clean separation. The rotation we have built our calendars around is a current condition, not a permanent one. The magnetic field that shields our biosphere is a current condition, not a permanent one. The tectonic configuration that has given us the current arrangement of oceans and continents is a current condition, not a permanent one. All of these things have been different before. All of them will be different again. The timescales involved are so long that they offer no practical threat to any individual human life, or to any generation now living, or to many generations to come. But they are not so long that a civilization capable of multi-generational planning, a civilization with the technological capacity to monitor these systems in real time and the intellectual capacity to model their future behavior, should regard them as irrelevant. The millisecond. That is where this story began. A millisecond subtracted from a day, registered by an atomic clock in a vibration-isolated laboratory, flagged as an anomaly in a dataset that most people will never encounter. A number so small it is genuinely difficult to assign it any intuitive significance. And yet that millisecond is connected, through a chain of physical processes that runs from the surface of the planet to its iron center and back, to some of the most profound questions in contemporary geoscience. Why is the inner core changing its rotation? What does its behavior tell us about the state of the outer core and the health of the geodynamo? How much of the rotational acceleration we are observing is driven by the deep interior, and how much by the surface redistribution of mass that human civilization is accelerating? What does a weakening magnetic field portend? A reversal, an excursion, a fluctuation that will correct itself within centuries? And beneath all of these specific questions, the deeper one: how well do we actually understand the planet we live on? The answer, delivered with the honesty that science demands, is not as well as we need to. Not as well as our instruments suggest we do. The precision of our measurements has outrun the depth of our understanding, and the gap between them is not a temporary condition to be resolved by the next generation of seismometers or the next improvement in core flow modeling. It is a structural feature of the problem, a reflection of the fact that the Earth's interior is, and will remain for the foreseeable future, the most inaccessible region of our own planet, known only indirectly, understood only approximately, its future behavior bounded only loosely by the physical theories and computational models we have built to describe it. This is not despair, it is orientation. To know the limits of your knowledge is not a failure, it is the precondition for extending it. Every accurate map of what we do not know is a map of where the next discoveries will come from. And the territory charted in this account, the rotating inner core, the weakening field, the millisecond scale fluctuations in the length of the day, the human contribution to polar wander, the coupling between the atmosphere and the oceans and the mantle and the core. This territory is being explored right now by researchers who are building better seismic networks, launching more sensitive gravity satellites, developing more sophisticated models of core-mantle coupling, and slowly, painstakingly, assembling a more complete picture of the interior of the world. But there is something that science alone cannot provide. Something that the data, however precise, and the models, however sophisticated, do not by themselves produce. It is the felt sense, the lived, embodied understanding of what it means to exist on a planet. To be not just on it, but of it. To be, at the cellular level, synchronized to its rotation through billions of years of evolutionary history. To carry in your body's daily rhythms, the imprint of a turning world. To have your capacity to exist at all depend on an invisible magnetic shield, generated by the churning of iron you will never see, thousands of kilometers below anything you will ever touch. The Earth is turning right now, as it has turned every moment of every day of every year since before the sun was old enough to have planets. It is turning slightly faster than it was last year, for reasons that are still being debated in the journals of geophysics. Its magnetic field is shifting, its core is rearranging, its ice is melting into the oceans, and the atoms of iron in its liquid heart are tracing convective paths that will eventually reorganize the invisible shield that keeps the cosmos from reaching us too directly. All of this is happening below the threshold of human sensation. None of it will interrupt your day. None of it will make the sky look different tonight. And yet it is all happening. It has always been happening. The planet is not the stable platform we imagine when we drive to work or plant a garden or speak of the future, as if the conditions that make the future possible are guaranteed. The planet is a process. We are a process inside a process. The ground beneath your feet is 4.5 billion years old and is still, in the deepest sense, becoming. The most ancient thing you have ever stood on is still changing, and we are only just beginning to understand how to listen to it.